In this example, we want to look at a theorem from linear algebra that describes basis vectors. So the theorem says if V is an n-dimensional vector space, we're going to let S be any set in V with exactly n vectors. The theorem then concludes that S is a basis for V if and only if either S spans V or S is linearly independent. By definition, we know that if S is a basis for V, then necessarily S both spans V and is linearly independent. So here we need to show that given that we know V is an n-dimensional vector space and S is a set of n vectors, it suffices to show that either S spans V or S is linearly independent. That is, we need to show if S spans V, then necessarily S is linearly independent, and if S is linearly independent, then necessarily S spans V. So let's suppose that S spans V. And let's further suppose that S is linearly dependent. Well, this means then there exists some vector in S such that when we remove this vector from S, the remaining set still spans V. That is, the span of S minus V equals the span of S. So now we have a set of n minus 1 vectors that span V. This is a contradiction then, because we know that the dimension of V equals n, and by definition of dimension, we necessarily need n vectors to span the space. So we conclude that if we have n vectors that span our n-dimensional vector space, then necessarily S is linearly independent. Now we suppose that S is linearly independent, and we need to show that it spans V. So let's suppose not. Suppose that S does not span V. Well, this means that there exists at least one vector in V such that V is not in the span of S. Which means that when we add V to the set, so S union the vector V, this new set is still linearly independent since V is not in the span of S. So here we have a set of n plus 1 linearly independent vectors in V. Well, this is again a contradiction since the dimension of V equals n, which means that we can have at most n vectors that are linearly independent in V. So we can conclude that if we know that the dimension of our vector space is n, and we're given a set of n vectors that we assume to be linearly independent, then necessarily S spans V. So we're done. And this theorem is very useful because if you know the dimension of your vector space and you're given that many set of vectors, then you don't need to check both spanning and linearly independent. You only need to check one.